Alright, so I was just getting number 27 and 5.2 set up before we get into 5.3. So number 27 just says we want to prove that the integral from a to b x dx is equal to 1/2 times b squared minus a squared. So let's see if we can prove that. So we're going to be setting up our Riemann sum, and so the width of each rectangle will be b minus a over n. The ith right endpoint will be a plus I times b minus a over n, right? So we're adding I of the widths to that, and then the height, our f of x is just equal to x, and so this is just going to be the height. Good. So now we can take the limit as n goes to infinity. Actually, before we take the limit, let's just go ahead and write down what the Riemann sum is and see if we can simplify that before we do anything else. So we're summing our rectangles together, a plus I times b minus a over n. So that's the height, again, height, and then the width is b minus a over n. Okay, and now if we simplify this algebraically, I'll have the sum. Maybe I'll get rid of that so I can write straight across. So that's going to be a times b minus a over n. And notice that this term right here doesn't have an I in it. Right, and then we'll have plus. I'll go ahead and bring in the sum too. The sum, I equals 1 to n of b minus a squared over n squared times I. Good. And so now let's deal with this algebraically before we go any further. So this first term is going to be a times b minus a over n times the sum of 1, right? Second term is going to be b minus a quantity squared divided by n squared times the sum of I. Good. And now we realize that these two things we have formulas for, right? And so that means we have a times b minus a divided by n times n plus b minus a squared over n squared times n plus 1 divided by 2. Good. And so let's see if we can simplify that a little bit. The n's cancel. This n cancels with one of those. And so we have ab minus a squared plus 1/2, and then b minus a squared over 2. Oh, I took the 1/2 out. B minus a squared, and then I have the n plus 1 over n. Good. Now what does this quantity represent? This is the sum, the area using n rectangles. Good. So how do I find the exact area? It's going to be the limit as n goes to infinity of a sub n, which in this case we only have one place where n appears, which is right here, and that limit is just going to be equal to 1 as n goes to infinity. So therefore this won't be too hard to write down. ab minus a squared plus 1/2 times b minus a squared. Good. What did I want? I wanted to see if this is b squared minus a squared over 2. So we'll need to do a little bit more work and go ahead and expand that other term there. So ab minus a squared plus 1/2 times b squared minus 2ab plus a squared. Good. It looks like we have ab minus a squared plus b squared over 2 minus ab plus a squared over 2, and those cancel. These cancels, leaving me with minus a squared over 2, right? And so therefore I have b squared over 2 minus a squared over 2, which is what we want. Good. So therefore we have shown that the integral from a to b x dx is equal to b squared minus a squared over 2. Similarly, we should be able to show in exercise number 28 in 5.2 that the integral of x squared dx is going to be b cubed minus a cubed over 3. Good, so see if you can do that one. That's a little bit trickier. The algebra is a little bit longer, but it's not too bad. Good, all right, so let's, sorry about the squeaky chair. Let's go to section 5.3 now. Before we talk about the main topic in 5.3, I wanted to talk about a special function, and that is a function called the area function. And so the area function is really, in general, what we're talking about is a function of the form a to x f of t dt. And so geometrically, what is that? That's a function that starts at a, and it's going to measure the area under f of x, or f of t, I should say, between the value a and the value x. Right, so as you vary x, right, you can compute the different areas. And so let's see if we can do this in particular. Let's call this a1 of x, and we'll write this as the integral from minus 1 to x of, well, let's do 2t plus 2 dt, just for fun. Okay, and I'm going to pause for a second and draw the picture. Good. Now, if I'm sitting here at x, right, can I write down what my area function will be? And you can see it's just going to be the area of this triangle here, right? And so the base is going to be x plus 1, right? And then the height will be 2 times x plus 1 plus 2. Oops, sorry, just 2x plus 2. Good. So therefore the area function is equal to, let's go ahead and just write it here. This is going to be equal to 1/2 times x plus 1 times 2x plus 2. So notice that the 2's, that I could factor this 2 out, and then this would just become an x plus 1. And so this is actually just x plus 1 quantity squared. Good. And so we could leave it in that form, or you could go ahead and write it as x squared plus 2x plus 1. Okay, let's try another one just to see what happens. Let's see, how about the area from 1 to x of t dt? What would that be geometrically? Well, here's my function, t, and then if I'm going from 1 to x, right, it looks like it's going to be the big triangle minus the small triangle. The small triangle is a 1 by 1 triangle, so that's going to be 1/2 there, right? So it looks like then my area is going to be let me pause and write it down. Good, so the base is going to have a length of x here, right? So the area of the large triangle is x by x, so is 1/2 x squared. Subtract off the area of the small rectangle, it's 1/2 times 1 times 1. Good. By the way, in this problem up above here, we already solved for that, right? So using this formula, I could have also said that I could have just plugged it in, right? 1 to x t dt is equal to x squared minus 1 over 2. Good. All right. And just as you're considering this, notice that a1 prime is equal to what? 2x plus 2. And what is a2 prime? 2 is just x, right? And notice that 2x plus 2 was the original function here, and x was the original function here, but with an x in it, right? So if this is f of t, right, this would be your f of x. And if this was let's say g of t, then this is g of x. Good. So what we're doing here is we're kind of setting up the background for something called the fundamental theorem of calculus. And it's really the big theorem for the course. So I'm going to pause here and set up, well, I guess I'm not going to pause, I'm going to stop this video, and when we start up the next one, we'll jump right into the fundamental theorem.